So this is the stress that's going on at point x is equal to 0.8. Okay. It's important that we calculate these constants. Okay, I highlight it's important that we calculate all this. Oh, I did not calculate down here. Sorry, I should calculate it. So later on it'll be easy. Oh, hold on. Bye. Okay, we should calculate. Let me elaborate what do I mean. I think we have to. So this is equal to 80 times 10 to the power 3. And then the coefficient, the three terms merge together, because later on when we do the calculation again, we don't need to press our calculator so many times. 40.1 power minus 6 divided by 6.35 power minus 3, close bracket, is 6 divided by 40.1 power minus 6 divided by 6.35 power minus 3 is equal to 498,714. Because later on when we calculate other position, that coefficient is going to be the same. Okay, so 39.897. Okay. Why I say it's important, because later on you'll see we will need this number, and we also will need this number for other location. Okay. So now this is x is equal to 0.8. Okay. Now we are going to next look at x is equal to is equal to 2.4. Okay. So from here you don't immediately jump to a conclusion to calculate the principal stresses. Okay, you don't do that yet. Okay. So next we are going to look at this point over here. Now this point is very interesting, right? Because at this point you have zero what? You have zero shearing stress. I repeat again, you have zero shearing stress. So now our element is loaded in such a sense that it only has what? Stress X. Okay. So if it only has stress X, okay, if I were to copy, if I were to look at the I-beam, right? If it only at stress X, right, maximum stress will occur here. Right? It does not have any shear at all. So for this problem, at this location, you don't calculate the junction, right? Because if you calculate the junction over here, if you calculate at the junction, you will not have the maximum stress, right? Because why? Your shear force is equal to what? 0. Can you see that? So for this case, to calculate at this point, to calculate our stress max or stress X, okay? And for this case, you have to determine the max. Okay? You have to determine the max. So this will be equal to the moment, again, is 48 times 10 to the power 3. I need to get the whole table. Okay. Okay. So now your y distance changes. Okay. So the y distance change, right, is changed because now your y distance, the z is still the same. The izz is still 40.1. Right? And then from here, we know that it's equal to what? We are going to find d 0.259 divided by 2. Right? So from here, we get what? 48 power 3 times by 0.259 divided by 2 divided by 40.1 power minus 6. This is equal to 155.012 times 10 to the power 6 Pascal. And this is our stress M. Okay, our stress M, as you can see, is the actual value. So this is our stress M we're looking about. Okay, and this is due to bending moment. The stress due to bending moment is stress M. So we located a point where bending moment is maximum, shear stress is equal to 0. That's how you find your stress M. Okay, so we know that this is equal to what? 155.02. And from here, we are going to look at our third point. Okay, so our third point is basically this point over here. Now, third point has a what? Has some has shear also, right? So again, what we're trying to identify is we know the loading is under this configuration, right? So from here, we know that stress X, all you need to do is take the 32 times 10 to the power 3. And then remember I told you that multiply by 2.98. Okay? Multiply by 2.98. You don't need to calculate again. You calculate before. So this is equal to 32 power 3 times by 2.98 power 3 is equal to 32 power 3 times by 2.98 power 3 is equal to 95.36. And then your shear XY is equal to 40 times 10 to the power 3, right? And then you have what? 498.714. 498.714. 498.714. That's why you calculate those coefficients. You don't need to press your calculator again. So it's equal to 19.948 times 10 to the power 6 Pascal. Oh, this one's also power 6. Okay. So now if we were to now look at X is equal to 2.4, when X is equal to 2.4, you have 398.897. The normal stress is only what? 47.68. Okay. If you look at X equal 3.2, your normal stress is much higher. Your shear stress is lower a bit. Okay. And if you look at this value over here, right? If we were to sketch Mohs circle at X equal to 0. Equal to what? 2.4. When we sketch it out, right? This is our normal stress. This is our shear stress. This will be our point X. This will be our point Y and also our point Z. So already, if it's under uniaxial loading, right? This value is our what? It's our principal stress, right? There is no shear. Where X is equal to 3.2 is not its principal orientation. Okay, so we have to determine our what? Our principal stresses. Okay, so now we are going to sketch, just sketch. Okay, you don't need to draw because the sketching does help you calculate your Mohs circle values. So you know that this is normal stress and this is our shearing stress, right? So I think we did the sketch earlier. Okay, so you know that this is our stress X. Okay, stress Y and stress Z are here. You know that this is our Z point, and then we cut here again. This is just a sketch, right? And then clockwise, anti-clockwise. So this is our point X. This is our point Y. And we realize that this is going to be the biggest circle, right? The in plane is going to be biggest circle because the out of plane are going to be your what? Your smaller circle. So now to compare, you have to compare what is at your you have to determine what is your stress A. Okay, you can don't consider stress B, but it's okay. So the first thing we do, we are going to find, so this is our mole circle, right? We are going to find what is our stress A, or we also can find what is our stress B. Why I draw this in 3D? Because we have to identify is the biggest circle in plane or out of plane. Okay, so the biggest circle is in plane. Okay, so from here, we calculate our center of circle. Okay, which is our stress average. So this is equal to 95.36 plus by 0 divided by 2. So 95.36 is equal to 47.68. And then we calculate our radius of circle. So what we have identified now, okay, if some of you are not sure, we have identified like this distance from here to here is what? 47.68. We know our shear is equal to what? Our shear is equal to 19.948. So we can find our radius. Okay. So from here, this is our tau max. So this is equal to 47.68 times 10 to the power 6 squared plus by 19.948. Go on. I should not rush. Okay, I'm rushing. So radius of circle. So tau max. So the whole thing square root 47.68 times 10 to the power 6 squared plus by 19.948. Okay. So this will be equal to 47.68 squared. 47.68 squared plus by 19.948 squared, and then square root the whole thing. I get 51.684. Did I get 5147.68? Wait, 95.36 95.36 divided by 2. 95.36 47.6. So 47.68 6 squared plus by 19.948 power 6 squared. Square root the whole thing is equal to 51.684 times 10 to the power 6 Pascal. So stress A and B is equal to 47.68 plus minus 51.684 times 10 to the power 6. Okay. So 47.68 plus by 51.684. This is equal to 99.364 times 10 to the power 6. Right. And then the other one is 47.68 minus 51.684 minus 4.004 times 10 to the power 6. Okay, so 10.68 and 9.364. Okay. So you realize that at point 155.02 or 155.012 times 10 to the power 6 is still the highest. Okay. So the next thing we have to do, we have to consider x is equal to 0.8. Okay. Because now you have a very high shear force, and the formula is all the same. I mean, wait, when I say all the same, it's similar to the one that we had just done. Okay, so this is our element again. I'm not going to draw more circle. We can just plug in all the values. This will help you reduce your time in your when you're doing your question. So now this is equal to 16 times 10 to the power 3 multiplied by 2.98 times 10 to the power 3. So 16 power 3 times by 2.98 power 3 is equal to 47.68 times 10 to the power 6 Pascal. And then the shear is equal to 80 times 10 to the power 3. And then multiply by 498.714. Right? So 80 power 3 times by 498.714 is equal to 39. So it has a very high shear stress. You can see that, right? Times 10 to the power 6 Pascal. So when we calculate the center of the circle, this will be equal to our stress average. Okay, center of circle. So the same procedure, okay, center of circle. Uh, 47.68. So 47.68 is here 23.84. And then the shear radius of circle is your tau max. So this will be equal to 23.84 times 10 to the power 6 squared plus by your 39.897. So 23.84 power 6 squared plus by 39.897 power 6 squared. Square root is equal to 46.477 megapascal. So your stress A and B will be equal to 23.84 times 10 to the power 6 plus minus 46.477. So this is equal to 3.84 power 6 plus by 46.477 power 6 is equal to 70.317 times 10 to the power 6 Pascal. And the other value is 23.84 minus 46.477 is equal to minus 22.637. So the highest stress, principal stress is 155,012 times 10 to the power 6 Pascal. Okay. One problem close to 1 hour 35 minutes to solve. Okay. As you can see, you have a lot of different layers, right? Like what I told you guys, right? You have to locate the position of the element where failure will occur. It went longer a bit because I was teaching you all, helping you all to recall your bending moment diagram, shear force diagram, okay? And then we apply 3D mold circle, right? We apply 3D mold circle. We apply our bending moment, shear force, 3D mold circle to calculate our principal stress. I'll still be around. I'll see you guys next week.